Our next speaker is Bo Billett from Edward Orton Jr. Ceramic Foundation, close to us here in Westerville. Bo has a PhD in Material Science and Engineering from The Ohio State University and is currently laboratory manager for the Orton Materials Testing Department.
We do primarily testing of refractories, but we also do a lot of glass testing. And throughout the presentation, kind of show where we can meet together and kind of use our tools and capabilities to help you guys solve some problems or even do some quality control, kind of walk you through what we do at Orton, a small fraction of it. Well, I wanted to start out with one of the first things I like to think about. I joined Orton about a year and a half ago, and one of the things that pulled me to it was the idea that it's a non-for-profit foundation, yet we are operating like a small business. So we get to do some really good stuff for a lot of people, and there's no issues with generating a profit. There's no issues with, making sure that the different businesses can grow and expand too quickly. So it's a good place when you start thinking about testing. If you're sending your samples off to a test lab, you want to make sure that test lab is the end of the day, our main goal is to give you a quality result. That's a very powerful thing is, you don't have to think about profit, you don't have to think about biases or anything. We are there to essentially serve you guys. So one of the founding principles you can see here, Edward Orton Jr. said, "A man working by himself, no matter what his habits of industry or study may be, can never achieve his true potential without association with others who can appreciate the value of his ideas." So Edward Orton Jr. was a force when it came to ceramics. He helped start the first ceramic society, as well as the ceramic foundation and the ceramic education at Ohio State University. When he passed away in 1932, his trust set up a foundation. That's where the pyrometric cone company was converted into the Edward Orton Jr. Foundation. And from there, we've produced the tiny pyrometric cones for the last, prior to 1930, it's been over 100 years of production, but started in 1932. Moving along throughout the years, we've expanded, and Orton Foundation purchased a test lab and also an instruments division. So that's kind of where we'll get into today, is with the instruments and the testing that we do with them. So the primarily focus of today's talk will be diatometry. So what I'll do is I'll give you a brief overview of what thermal expansion contraction is, how it relates to materials, and then I'll jump into the key components of a diatometer, kind of how it works, what it measures, and even though it's a very simple measurement, there's a lot of kind of different moving pieces that go into it. Follow that up with the sample preparation and then the following test procedures that we use to conduct and make these measurements. Touch on calibration briefly to show you how important that is, and then finally wrap up with the materials we measure and kind of an example of what this can do for you and how it can solve some problems that you guys might come across in your daily work. And then kind of finish it up right there at the end with how much is it going to cost, because at the end of the day, it's great and dandy until you can kind of work it into your business plan and see that it can possibly work for you. So thermal expansion contraction is a fundamental material property. Material properties, they have three main thermal responses. So as you heat up a material or you expose it to an environment with temperature, you can get three main responses that all interact and affect how that material is going to perform or how that material is going to transition when you go to use it in product. The three main ones are volume stability, which is what we'll talk primarily about today, heat capacity. So that's how much energy can be stored per gram at a given temperature of a property. Very powerful. We do a lot of testing with that with DSC and also a lot of calculations through that. Finally, thermal conductivity. Now that's more of a production process route. You want to make sure that your refractory brick or your ladle for the glass production is going to reach the temperature you set, and also kind of have an understanding of how much power is it going to take me to maintain that temperature and go ahead and continue that process. Those are different talks and different concepts, but feel free if you have any questions to reach out to me. We do testing in all three areas, and all three are very important to processing, especially with glasses. But today we're going to focus primarily on volume stability. So there are two main aspects of volume stability. That's the reversible changes that you see material respond to, and also the irreversible, the permanent changes. which may not always be that bad. You know, you kind of need to drive a reaction. Your end goal might be an irreversible change. But a lot of what we see will be reversible changes. So this is predicated, and this is based on just simple nature of the vibration of atoms. So Einstein's theory, spring constants and all that, at the end of the day, as you heat up something, the atoms are going to vibrate more and more. So this vibration amplitude is going to increase the distance. Now, based upon the material you're working with, you know, this could either lead to a large stretching, a melting, or even a decomposition as the bonds start to break past their elastic limit. So based upon that, you kind of start to think about just the fundamentals. So if it's based on bonding present, just two really broad examples would be, if you look at covalent bonds, which are strong, that's kind of the stuff that you see in ceramics and materials. So based upon just a broad example of these different types of bonding in materials, you look at covalent bonds, which are strong, and therefore you have low expansion. A lot of the ceramics will experience as the refractories, they end up decomposing, if anything, over time. Where if you look on the other end of the spectrum with your metallic bonds, they're much weaker, and so you have higher expansion and eventually go to melt. So that's the one end of the spectrum. The other end of the spectrum kind of looks more at the microstructure, the irreversible damage, permanent changes. Not necessarily damages, but you know, more often than not, it's kind of an unpredicted, you know, thing to occur. So that's when you have a microstructure that's not at equilibrium. So something is not happy with the state that it's in. You provide energy, which gives it mobility to move the different phases to where they want to be, and therefore they can create different chemical reactions, form a new compound. It can even possibly, as you move these molecules around, you actually can decompose and release gases into the system. Or, you know, on a positive note, you can actually, if you have a seed for a crystal that you want to grow, the nucleation and growth starts to occur, and you expand these grain sizes. Or finally, reverse of that, instead of expanding and growing larger grains, you can center, which, you know, you remove the porosity and you have a more dense product in the end. So those are just very large brush strokes to kind of understand just some of the different categories that your materials can perform in when you're analyzing them for thermal expansion contraction. So how do you analyze them? With a dilatometer. Orton makes dilatometers, Netsch makes dilatometers. There's a wide range of these different products that you can purchase, but at the end of the day, they all kind of used to. Some of them have a little bit more different capabilities now with the different types of nanoeyes and the different optical and non-contact measurements. But at the end of the day, the simple principle is such that you have a furnace that creates the hot zone. So you want to make sure that your hot zone is plus or minus, I believe 3 is the spec, but you want to have almost an isothermal across the length of your sample. So we'll get to sample prep in a little bit. You'll see how that kind of works into it. But over the length of the sample, you want to see the same temperature because you're looking for a temperature response and you don't want to have a gradient inside your sample. So does this have a laser, probably?
I don't think there's a pointer on it, that just advances.
No. Well, you can see here that you have the sample across the length of the sample. You could possibly have movement. Now, LVDTs, the other key component here besides the furnace is it's a linear variable differential transformer. Everyone calls them LVDTs. What they do is they'll take that movement and correspond it into a given electronic signal. So from there, you can see how far the sample's moving. LVDTs can't work in a high temperature environment. Not much can work in these high temperature environments. You're looking at your material response in a very basic rudimentary form. So no electronics are going to go into this furnace. So what your main goal is to measure this, you have to get that motion outside of the furnace. So you're going to use just a really simple rod, contact rod. It's just a piece of alumina, a piece of fused quartz. It's something that is going to expand and contract a minimal amount to transpose the movement of your sample in the hot zone out to a friendly atmosphere in which your LVDT can make the measurement. Really simple, really rudimentary, but at the same time, a very powerful tool to see how your materials will respond at different temperature, heating rates, cooling rates, different hold times. So you can start to see how your temperature is going to respond in a very simple, primitive, linear motion. So what does a real one look like? We have one here. This is the model 1410. This is the standard dilatometer. Over the years, they've gone through different design features, they've had different add-ons. But at the end of the day, it comes down to your LVDT on the far right there, with you have a micrometer to set it in place. LVDTs have an expansion contraction range, so you want to make sure that you set your sample up to give it the largest amount of working area. Then you have here, you have your push rod. This one looks like it's a fused quartz push rod, and then right here in the center you'll have your sample. So this sample is quite exaggerated just to kind of show you what it looks like, but in something like this, you'll see in the sample prep section that the sample is about 1 inch long to maybe 2 inches long. And then you have your furnace that closes over top of that, heats up your sample, and this all goes to a computer controlled device where you can make sure that you are collecting the data as you are heating and cooling the sample. How do you make the sample? Like I said, this is a very rudimentary, fundamental thing and just linear measurement. That being said, you want to make sure that you have parallel surfaces. You don't want to have any sort of edge effects or expansion or contraction in different orientations that would take away from the measurement. So parallel surfaces, this is not your table saw. You're not going to go home and cut the molding for this. This is something you use a little bit more advanced equipment. You have the low speed diamond saw here with a micrometer on the end of it. And you want to make sure that you're not moving the sample once you put it in the grip. You want to make a cut, turn it, make another cut, and be done. You're not eyeballing it, you're not taking it on and off. You want to sit there and make a very clean cut to make a very parallel surface. That, or sometimes we have to employ the use of a grinder, which gives you very parallel edges where you sit there and use a mechanical grinder to actually parallel the surfaces. From that, the other thing to think about that you want to keep in mind is the calibration accuracy. Okay, we'll start about calibration in a second here, but you want to have your sample be the same length as your calibration standard. So when we're looking at materials, we cut them to 1 inch. And when I say 1 inch, I mean 1.000 inches. And we're calibrating against a platinum rod that is 1.000 inches. Those are very important because when you see here in some of the graphs, we're looking at very small changes over the course of the measurement. Typically, there's a lot of other cutting. We see the low speed diamond saw here, but you usually have large, almost like what you see on the highways with the guys with the big diamond saw blades that cut the concrete. We have a couple of those tabletop, and we'll do the prep. We'll take it down from a large refractory or even a chunk of glass. Glass is really fun to cut, no matter where you are. It's going to fracture, and it has its moments. Or there's also a different prep method where you go from the frit and you can go and create your sample with the net shape that you want to use. A much better way to go into this. You'll see that here in a second. Wet versus cut versus oven dry. This starts to kind of allude to it is a simple measurement, but there's a lot of things that go into this. You want to make sure that is the sample already fired? Is water going to cause some sort of hydration reaction or anything? So it's not simply a sample. It's not something you want to throw to the side, cut it, and put it in there. You want to give a lot of thought to see what your sample is going to look like and how it's going to respond. In order to do these accurately on industry scale, I'm not sure if you guys are familiar with ASTM, a very large organization, provides test standards across industries. And for this one is the ASTM E228. That's our primarily mode that we operate with. It dates back to 1963. And what this does is it provides a means to measure it in a way that everyone else is going to measure it. So if I give you a CTE on a piece of a material that you send in, sample 2A, 1, or whatever, if you were to send it to another lab, the idea is they would perform the same means of testing and provide the same results and really give that result a lot of credit. Minus 180 is not a typo. We do go down to liquid nitrogen temperatures. It's always fun in lab to have the smoke bellowing out. You see stuff going everywhere, but that does provide a lot of measurements for a lot of the glass industry for the 0 to 300 measurement. That's still a low room temperature, so you have to use a cooling mechanism. We do some different testing for some more of the advanced materials that get down to space applications and stuff, where out there they're going to see a lot of things, a lot of temperature variation. You can also go up on the other side up to 1600 C and also up to 2500 C. We actually do not currently have the capabilities to do 2500 C, but if there's a large demand for that, we would be happy to look at that. I don't know what the temperature, I imagine you guys are topping out at maybe 1400 C, 1200 C, 2600 or 2500 C is up there. As I said, these measurements are very small, so your linear expansion is typically referenced in parts per million, being not a concentration, but as a 10 to the negative 6 unit. So you have inches per C, or centimeters per C. And that's because you're relating it to the sample length itself. It's a percentage. So it's not a tool that says, okay, you will be able to predict what your sample is going to see in the future, but the measurement's made per inch. So it's how long of a sample is contracting how much. Very important. I don't have any slides on it today, but heating rate and cooling rate has a large effect on this. So if you are heating it up at a faster rate versus a slower rate, you're going to see a slightly different measurement. So it depends upon your application and how you're going to be using the data. And this one is just the most commonly referred to one. This is, we'll get this for people from the nuclear industry to the refractory industry to the metals industry. The E228 is a very robust test that covers a lot of questions and details. Alternatively, I put this in here today. We don't reference this as much, but this is specifically standard for whitewares, glazes, and porcelain animals. They are practically interchangeable standards. They both use the same techniques, same equipment. This one does have a little bit of sample preparation explained for if you're using a frit. It talks about a mold and how to pack the mold to make sure that you get the correct answer. So this one's more industry specific. Other than that, though, it's the same test method, and we can run both or even provide results for both if needed. So at the end of the day, what does all of this look like? Well, it's a very simple curve. Temperature on the bottom, percent change on the y-axis there. So these are different calibration materials. As I said earlier, it's very important when you calibrate it to have the same length of sample. You also want to have a calibration that's in the same regime. So if you're going to be testing a material, something like copper or a metal, platinum and copper, you're going to want to calibrate against the standard that's going to experience those same percent changes, because if kind of like making a measurement, you want to make sure that you're making it on the same length scale. So you're not going to use a ruler to measure the length of this room. You want to go ahead and use at least a yardstick. I'm not sure if one of those rolling things are really nifty, but you want to make sure you're using the same scale of a material to make these measurements. Platinum, though, is robust. It does both. You can see it's almost very similar to alumina, the ceramic, and it's also really similar to copper, and it's pure metal itself. So platinum is kind of our wheelhouse. It's the one we go to with mostly. It's a very linear curve, and it's also nice because you take it up to a very large temperature range, up to 1600 degrees C. So with that being said, platinum's your wheelhouse. You can do low temperature, high temperature with all the same material. We do calibrate against borosilicate sometimes, and also fused silica, and you'll see here in a presentation here in a minute the difference of rates, how those can look against each other. At the end of the day, we do this calibration, we do the sample prep. Here is what your report is going to be for Morton if you were to use our testing services. It's a really straightforward 2-page report, 3 pages, depends on how many temperature measurements you want made. But here on the left is similar to the calibration runs. This might even be a metal itself. But you can see that you're going to have a percent linear change on the left side in the temperature range. So you can start to understand where your material is going to perform. You can say, hey, and I'll show you some examples of different materials. You can start to qualify, hey, is my material what I think it is? Is it going through any transformations? Is it expanding too fast? Is it cooling too fast? You might have a mismatch with my body glaze fit. So it starts to it's just a tool to start to help you understand your material performance and response. Because at the end of the day, most of these glasses and frits, you're going to be exposing them to temperatures to bake them on, cure them on, and all different types of techniques. So how is your glass going to perform at temperature? This is kind of your key. It's not everything, but it's a very simple, straightforward measurement that you can do to start to understand what kind of response you're going to get at different temperatures. On the right, a little bit more detailed, more of the tabular version of the data, same data, but what it does is it breaks it down into different temperature ranges. So you can see that in that one, it looks like there's 20-degree jumps. So it shows you that, it shows you the rate that we took it. So this one was reheated at 3 degrees C per minute up to 1,000 degrees. And then you can see that at 160 degrees, you have a permanent linear expansion, of 0.227 inches. 0.227%. So what does permanent linear expansion mean? That means how much it's changed permanently until you cool it back down. So at that temperature, that's the length expansion you're going to see. Then the next column is the alpha CTE. This is the more powerful measurement. This is the material property. So this is based upon the length of the sample originally. This is in the temperature range. This is where you start to qualify different materials for different CTE values. So as I was showing you earlier, platinum has a plus or minus range of 8 parts per million per degree C. I think actually it's 10, but it's plus or minus 2. So you start to see an actual very definitive number to say what a material CTE is. We'll see in a second the calculation that goes into it and how you can kind of start to, it's not as straightforward if you have a material that's not performing quite like this. You can see here, your CTE, it starts off at a slightly different range, but it kind of levels out right around 17, 18 parts per million per C. So with that, you can see a linear performing material, but they start to slope or curve, and so you have to understand what range you're looking at. So, as I alluded to earlier, the thermal expansion contraction is the primarily material measure. That's not a performance parameter, that's not a bulk response, that's not something you say at the end of the day, what's your thermal expansion contraction is, but that's what we're measuring. From those measurements, we can deduce whether or not there's a phase transformation occurring in the material. We can also start to qualify how the material is performing or how it will perform in my application. And the 3 major outputs that you get for a diatometer would be the CTE, as we saw in the graph. And then additionally, we can label the glass transition temperature if we're measuring a glass, or a material softening point. So those are very important material properties. There are different techniques. There's other types of means to measure those, but those are added values of running the diatometer. So phase transformations, what would those be? I pulled this one. A lot more of our phase transformations deal with refractories and refractory materials, where you have a lot of things occurring. You have a lot of different types of dirt mixed together that you're going to fuse into a refractory brick, and different things can occur. With glasses, I kind of pulled the quartz one here. It seems relevant. And what is a phase transformation? It's the atomistic movement to stable crystal structure. So this is where phase diagrams are really a good tool. If you guys have ever used those before, you have the different concentrations, the different temperature ranges. And from there, you can see what is going to be the stable phase at the different temperatures and compositions. That being said, it is a very important, it's a temperature and time dependent thing to occur. So time is a factor there. We don't really talk about it too much. If you hold something in a prolonged time, it provides enough energy for kinetics to occur, and some things will happen that wouldn't happen on a shorter time scale. So that's always something to keep in the back of your mind especially if you're a glass processing facility. I imagine if you have a refractory brick or a ladle, over time, it might not be seeing the high temperature that it's the max use, but it's going to provide enough energy input to eventually reach a stable phase if it wants to. These are different types of phase transformations that can occur. You have listed at the bottom here, I've listed a couple of the different volume expansion contraction measurements. So how do we know if it's high quartz or low quartz? Well, we have the temperature there. This occurs around 573 degrees Celsius, and it's correlated to about 0.9% volume expansion. So now when you run the diatometer and you get your CTE and your actual permanent linear change, you can see, is that in fact, it's at 573, how much material is quartz? You can start to kind of calculate that based upon what the volume expansion would be if it was pure quartz, purely quartz from high to low. So those kind of start to show you the complexities that you can use the diatometer for. At the same time, this is more of common in the different industries where you have a lot more phase transformations occurring. But don't let that deter you. It is something that's a very powerful tool. What would that look like in those reports that we provide? Here on the left, you see that there's a quartz transformation in a whiteware body. Right there at 573, you see the shift and on heating. And then on the right side, you can see another example from the slide I just showed you. On cooling, actually, it looks like it reached a high temperature and it allowed slight mobility, as you can see, kind of soften and bend over there. And then it actually, on the contraction, things are close enough to go ahead and react. And on your cooling, you're actually forming a combination of tritonite and cristobalite from the fused silica. So once again, and I think I haven't alluded to this yet, but there's heating and cooling. So you can look at how material is going to perform on the heat up and hopefully no reversible, or all reversible changes. The cool down will be a very similar, if not identical, linear slope. What is the calculations? The beef of this is the coefficient of thermal expansion. How is it measured? It's really straightforward. It's a linear change over a temperature change based upon the initial linear length. The units, as I mentioned earlier, are in inches per degree C, or centimeters per degree C, or parts per million, given the fact that you're typically at 10 to the negative 6. So the part per million is not a concentration there, it's used as a ratio. The other two that we mentioned earlier, how do we calculate the glass transition temperature? You'll see it in a couple slides, but it's a graphical determination. So it's based upon where you select your range and how you select the linear slope. But both the glass transition temperature and the material softening point are graphical representations. So they're slightly subjective, but they're pretty consistent. They're pretty agreed upon in industry. As I mentioned earlier, the CTE, you need to have an understanding about how the material is performing. You can see here, this is all one material. This is one glass that was heated up to around a little past the softening point. And usually that's where we stop, because you're not going to go beyond that. The material is just going to soften and turn to mush. But with that, as you heat it up, you can see that there's a CTE right there of 9.98 from 25 to 300. If we go a little further, we jump all of a sudden, we can jump up to, it looks like 17.38. So along those ranges, there's different CTs that you can, it's a tangent material calculation. So it can be skewed one way or the other. So that's kind of, it's more to be understood with the actual graph in hand. You don't want to be looking at CTE unless you know it's completely linear. And a lot of glasses, they do have a lot of linear at the beginning, especially the anneal glasses, but there can be some different changes you see. I mean, it would not be really beneficial to say that the CTE up to 438 is 19.56, because not at one point along there, you actually have that CTE. Additionally, you have a CTE from 400 to 438, 993.62 parts per million. That's really high. That's not an actual CTE that would be valuable for this process. Because typically, based upon where you're going to be working with the glass, you're not going to be seeing expansions like that for a very long time. Much more powerful and direct correlation here for you guys, I imagine, is the glass transition. So this really starts to help out with the material processing temperatures and where you're going to work with your glass and where it's going to be applied. So here it shows you very straightforward. How do you calculate the glass transition from a diatometer run using two linear sections of the material, and you can see that it's at the convex of the curve where it starts to change and actually really start to act like a liquid. So there you can see there it's labeled at 410.54. So it's a very powerful measurement, an added value of running glass in the diatometer. Two different curves here. So as you see there, we can clearly label all the points with the annealed glass. You have the softening point at the tip, the glass transition from the convex, and then you have a very linear range for your CTE. So it really qualifies the material. It's not a big deal. We can easily add the labels onto the graph if you request it. Sometimes people like to make their own judgment calls of where to pick the curves. On the right side, this goes to show you that the material performance is relative to the material itself. So you're looking at this, silica versus fused silica, very similar materials, but not when you are using them in a large temperature range like this. It has the fused silica at the bottom hardly makes a move, while your silica goes through a large displacement reaction, and it kind of starts to show you which one should I use for my application. It kind of helps you figure that out quickly. So all of that's kind of the background of the different diatometer stuff, the basics of the measurement, the basic of the materials response. I'll show you these last couple of slides here. How does it apply to the glass industry, and how can it be beneficial to you guys, and what kind of problems it can help to solve or prevent. Well, here's an example of a variety of glass frits. These could look different, or they could have different chemistries, but at the end of the day, how they're going to perform when you go to use them at temperature. There, it looks like there's 6 different glass frits there, and they all have different responses. So this helps to pick which glass frit you're going to use for your raw production, or what you're going to use for your enamel, it starts to help you see that there's a different response, there's different temperature ranges for all of these. You can, the glass transition and the softening point where it becomes, workable, it ranges, from 400 up to 550 here. Additionally, you have different thermal, the expansion contraction, the CTE values, they have a large range in these too. So you can now not only help to pick which frit would be best or glass to use in your application, you can also start to use it as a quality control mechanism. You can say, hey, is this actually the frit that they sent us? You can run it through the diatometer and say, okay, it looks like it's behaving with similar properties. It is likely to be it. It's not a chemistry or an XRD or X-ray fluorescence. It's a little bit more, primitive than that, but at the same time, it does, relate to the material chemistry and the structure, so you can kind of use it as a rough way to ID a glass to kind of understand if it's going to perform how you want to. Here's an example of a quality control test. You have, I think this is an alloy of sorts, but you have the error bars provided, so you know that my material has to perform within the specs. So I go ahead and run on the diatometer. Does it fall within the line of the specs? Yes, it's good to go. So you can go ahead and release that batch of the alloy, or you can receive the batch of glass frit. It can really start to help you with quality control, and it's, I think, important because when you're firing or you're using these materials at temperature, not only is it a quality control based upon chemistry and identification, but it helps to understand performance. So it's a robust tool. Now, even further with the performance, you can start to see about glazed body fits. So right here, we have a really simple, straightforward 3 curves. You have the body in the black. You have the glaze that's a good fit in the blue, really cheery, happy, chipper color, and then you have the bad fit glaze in the red. And from this, you can see that the glaze is a little bit more forgiving during the alpha beta transition that your body's going to go through. So you want to make sure that your glaze can help to compensate for any sort of expansion from that transition. And then, as you can see on cooling there, as you hit 400, 300, the body and glaze are gonna shrink, contract in a similar manner. This is going to be very important when you look at compressive tensile forces on your glazed body. So if it's you prefer to have a little bit of compression to have the right amount of stress along there to have the little bit of strength, but you don't want to go too compressive because you're going to start to get cracking, as well as if you go too much tension among them, you're going to have a lot of blade crazing and cracking in your glaze enamel fit. So you start to understand that this diatometer has a powerful tool to qualify enamels before you even go ahead and purchase them. You can get a sample, you run your enamel on the diatometer, you can say, oh, that will work with the current formulation of the body that we have with our whiteware. You're not going to go, I imagine, to change the body, the whiteware formulation, or vice versa. If you change the enamel formulation, you want to make sure that you change them in such a way that they're both going to react well and minimize crazing and cracking. So those are a couple examples of how the diatometer can help with the industry and where you can apply it. At the end of the day, how much is it going to cost? Well, there's 2 options. You can purchase a diatometer, which we do. We do a very fair price, and we do make a very robust and durable diatometer. So after X number of runs, it could be an inexpensive option. And therefore, you can also use it for both, a material performance tool or a quality control tool on received material. And it helps to make sure that your final product is what you expect it to be, and helps to keep it internal and quick response to any sort of changes. That being said, it does make, you have to calibrate it and upkeep and make maintenance. This is something where you'd want to have a trained technician that understands the diatometer, that regularly calibrates it and make sure that those measurements that I showed you there are actually the material's performance and not an error in the measurement. So that is one of the drawbacks. Another option, depends on how many runs you're going to be doing. It might be the cheaper option, is the test lab measurements. That's where I'm standing here in front of you guys is a big help because we have a large bank, and I'll show you here in a second the different price breaks, but no capital investment, no maintenance. We, as I started the presentation with, we're a nonprofit foundation that, at the end of the day, our goal is to get the best measurement out to you guys. So we regularly calibrate, and that's, inherent and assumed. Depending upon which test lab you go with, you want to make sure that the calibration is done routinely, because an LVDT is accurate, and it's, but at the same time, you want to make sure that there's different expansion contractions that occur with your push rod and different things that take into effect. So you want to make sure the calibration is performed regularly. Kind of a negative, could be a positive, is the 2 to 3 week turnaround is a typical response for us. So it could still, depending upon how quick you're moving, or if the truck's on the dock ready to pick up your product, probably not a good quality control tool. But that being said, it still can be used as a quality control tool as you receive a raw material before you put it in the line, or if it's you have the product finished and you want to qualify it before you send it out to the customer. It could still be a QC tool if you're looking at a 2 to 3 week turnaround. So, as always, purchasing versus contracting it out, different takes to both. But we at Orton can provide a helpful, conversation, at least which way do you want to go. The cost, we have various configurations. I didn't provide any pricing on that here today. That's a large range that depends on your needs, and that's typically they don't provide numbers when it's on the larger end. These are straightforward. These are measurements that we have 3 going right now in the lab, and on Monday we'll have another 4 to do. So we do these regularly, and these are the different ranges and the different pricing that you can see here for the different tests. Now, with that said, I'll take some questions. I put up some contacts here. These would be really important for you guys to write down if you were interested in receiving a quote for the diatometer from Jim Baldwin. He is the guy that runs our instruments division. A really friendly guy, really knowledgeable guy. So if you have a question, feel free to shoot him how a diatometer could work with your application. For testing services, that's where I am. My immediate boss, who does a lot of the customer interaction, is Brian Rayner. Very knowledgeable man that's been in the industry for a long time. And as I said earlier, we're talking about diatometer here today, but at Orton, our testing is over 100 different ASTM standards. So we do glass viscosity, we do softening point, annealing point by fiber elongation. We also do liquidus measurement. So there's a large range of options there if you ever have questions or if you need a test done. Our prices, as I said, are very fair and straightforward, and we even have a price book on the internet where, instead of wondering, I wonder how much it's going to cost me, you can go directly to our website, and it will provide a brief description of the test as well as how many samples you would need and the price of that test. And that's about it. What kind of questions I can answer? How was it? On time? Yes?
When you talked about you had a lovely slide on the frets, how do you cast and machine a fret?
So for the frit, the one spec I didn't list up here would be the standard practice that we follow, and that's where you have a mold with removable sides. Depends upon the frit, but you can put a binder in there. You grind it down to a certain sieve size, pack it in there tightly, and then fire it and remove it from the mold, if that would be a preference to you. But sometimes people have different requests, but typically we would pack the frit into a mold to the net shape, fire it to a solid piece, and then go ahead and use that small 1/4 inch by 1/4 inch by 1 inch sample and make the measurement from there.
Thank you.
We'll actually melt some frets sometimes and pour patties,
Yeah.
and then anneal them and then cut the bars out of
Yes.
those sometimes there.
Machining glasses, it is difficult, but we have the capabilities, and we do it on a regular basis. So if it's something that you wanted a larger, if you're worried about any sort of edge effects in your material, we can cast a larger bar and cut it down as well, as he was explaining.